for arbitrary function, for arbitrary derivative. This is a perturbation term. You could take one trajectory of that derivative by the s. It's moving, it's kind of perturbing that, moving it in this direction. And so because you want it to be equal to 0 independently of that, then that term should be equal to 0. And that gives you the equations, which I already said how they're called. These are called Euler-Lagrange equations. So let me write it this way. So it's d by dt dl by dq dot I minus dl by dq I is equal to 0. So, of course, L is a function of Q and Q dot. If you compute this, you'll get a system over E. What kind of system? Well, L depends on Q and Q dot. There is time derivative here. So if you differentiate this, you'll get at most second derivative. So this will be second system of second order system of n second order or E. Right? Well, remember that example that I told you. Let's compute this for that specific example. I get m over 2, just some constant, and then you have q dot squared minus v of q. Well, this, of course, is a vector square. It should be good. So you need to compute this derivative. So you get dl by dq dot. So it is m over 2. And then take the derivative of velocity squared with respect to the velocity. So it gives you 2 q dot I. So that's it. This doesn't depend on it. Okay? And this derivative, because this does not depend on coordinates, it will be just the derivative of v. So you get, well, these two cancels, and you get d by dt m q dot I minus, there is this minus, and there is this minus, so it is plus. And let me put it on the right hand side, and you get e by dqi. Well, you probably saw these equations, well, depending on where you study, maybe in high school, maybe earlier. But this is due to the equation. This is m times acceleration, ma equals z. That is the force, that is velocity, take derivative, get acceleration, you get this. That's Newton's law. Okay? So if you take that Lagrangian, you get this. Take some other Lagrangian, you get another system, but it always that. Okay? So let's look at another example which is more interesting than that simple one. And by the way, this derivation, I mean, it's a trivial thing. The only thing I've done is just one integration by parts. Well, the way he does it, it kind of, if you never saw it before, it makes it a little bit complicated.
Just one question.
Yeah.
You went from a sum over I, and then you broke that up into each one having to be 0?
Yeah.
What was the reason?
Well, because each of the terms, well, okay, look, if you have sum of I, AI, BI is equal to 0, right? So there is sum. Now, if you want this to be equal to 0 for arbitrary V, then that implies that AI is equal to 0. Why? Well, because, well, you take V of this one, 1, 0, 0, 0. That gives you A1 is equal to 0. Then you take B is equal to 0, 1, blah, blah, blah. That gives you A2 is equal to 0, right? Because this arbitrary, then, well, what does it say? It says that two vectors are orthogonal. If this should be true for arbitrary vector V, then this must be 0 vector. There is only one vector that's orthogonal to all vectors. That's 0. Make sense? Okay. So, the example that I was talking about, well, it's called a particle, well, in the gravitational field or the curved manifold, let's say, on the random manifold. But I'll explain the geometry later. For now, this will be just some example. Here is your function that the Lagrange. Again, it's a kinetic energy minus potential energy. We'll assume that kinetic energy, well, this velocity square certainly is not an invariant object on the manifold, so we just need to replace that by an invariant quantity. Well, the mass is not that important, let's call it 1, it doesn't really matter. So it's 1/2, and so to make that velocity square invariant thing, you need the metric. So I'm going to Gij that depends on Q dot I, Q dot J. And there is some I and J. Where this Gij is real n by n symmetric non-degenerate matrix. Okay? Which depends on the position. So this is nothing but, well, this is called the metric or Riemannian metric. So why is it a metric? Well, because it defines an inner product like this. This is an inner product. This is a product of these two vectors between themselves. But of course, you could, by using that, you could define an inner product of any two vectors on the manifold. So that's the kinetic energy. Basically, the velocity is squared, but it's an invariant velocity. And of course, because of the metric, it depends on the position. Well, it's not exactly gravitational field because gravitation is described in general relativity. Well, it's such a metric, but it is not. Well, I didn't say that it's positive definite, so then it's fine. But in general relativity, pseudo Riemannian. Riemannian means positive definite. So this matrix is positive definite. In other words, it's all eigenvalues of it is positive. And it is invertible, I said it is non-degenerate. Okay. So, and then you could say we have some potential energy and some function, scalar function of Q, of coordinates only, independently of the velocity. So that's Lagrange. It describes, when people do say quantum mechanics on manifolds, that's exactly what you would do. And so, but also when you describe geodesics, you'll see that it's directly related to that. Okay, so what are these equations? We want to just specify that, you immediately have this. So you can write those. dl by dt by I. Well, let me call that k, because they already have I and j. So you're differentiating this with respect to velocity. So this doesn't depend on the velocity. So therefore you'll get 1/2 sum of ij, gij. And well, it depends on q, but I'm not going to write this explicitly. And then you differentiate this, right? So there are two of them, it's basically square, but you differentiate this and this. So you get 2 times it. So you get, well, let me do it in all details. So you get 2, and then you get q